Hello, this video is about why you should use a second derivative gain, or why PID 2. The second derivative gain is the gain that is multiplied by the error in acceleration, whereas the derivative gain is multiplied by the error between the target and actual velocity. So the significance of this is that without the second derivative gain, the person that's doing the hydraulic control, setting up the controller, is limited by the natural frequency and the damping factor, and he has no control over that. That's what the hydraulic designer and the mechanical designer have control over. And so sometimes the control person gets stuck in situations trying to get performance out of a system where it's just not possible. And this is going to be the proof that shows that using the second derivative gain can help the control engineer get out of a bad situation where the natural frequency and damping factor are low and still get good performance. So I'm going to start out. There's some practical limitations to this. Feedback limitations. In other words, when you trying to use the derivative gain is usually what people call noisy. Second derivative gain would be noisier. Now, actually, it's not noise, it's quantizing because you don't have infinite resolution on your feedback. And that can cause a problem. So there's a limit to how high or how much performance you can actually get out of a system based on the feedback resolution. Another thing I want to point out is that I am not the first one to come up with this second derivative gain. It was actually, I saw it first on an MTS TDC controller way back in the 1980s. Back then they only had 188 processors, didn't have enough CPU power, nor was there enough resolution to implement a second derivative gain correctly. So let's get started with the system. Okay, we're going to have the controller first, I guess. This is the Laplace transform for the controller. It's the second derivative gain, and then this is the PID part here, and this is the second derivative gain here. And then we have a type 1 integrating system, and we have a gain, which is the open loop gain. It's the how fast you're going to go for a particular unit of control output. Typical units would be, say, millimeters per second per percent output. And so if you had a gain of 10, that would mean that you, at 100% output, you'd go 1,000 millimeters per second or 1 meter per second. There's a natural frequency. There are formulas for calculating that, but basically the hydraulic system is a mass between two springs, and the system can oscillate. It does compress. Then there's a damping factor, and that's how much resistance there is to motion. So if this is the closed loop transfer function, the general form, and if I substitute for the actuator transfer function and the controller transfer function, I get this closed loop transfer function. That's kind of difficult to work with, so I'm going to simplify it till I get a closed loop transfer function with just numerator and denominator. And the significance here is the denominator is the characteristic equation, and that determines how quickly errors are going to decay to zero. So one of the things we want to do is choose the correct gains. Now you can see that there's a Ki gain here for that 0 power of S, a Kp gain for the first power of S, a Kd gain for the second power of S, and a K2 gain for the third power of S. And that's significant. Without this K2 gain, you're going to be able to see that we're going to have 1, 2, 3, 4 equations, and if we only have 3 unknowns, we're going to be limited to where we can place the poles. And what we want to do is place the poles as far to, well, in your case, as far as to the left as possible, so that any errors or transients decay to zero as quickly as possible. Now, to calculate a characteristic equation that doesn't overshoot, what we want to do is we want to start with 4 real poles. We have to have 4 real poles because our uh, open loop, or I mean our closed loop characteristic equation has got 4 poles. And we're going to have 4 poles, and they're going to be all real. They're going to be placed on the negative real axis, and that'll make sure that the system doesn't oscillate. It will just, it'll be like 4 low-pass filters. It'll just gradually get up to the target, or air will be reduced exponentially down to wherever the target happens to be. Now, to calculate out the gains, what we need to do is equate the coefficients for each power of s. So, for instance, here we have the 0 power of s, and that's k times the natural frequency squared times ki, and that needs to be equal to lambda to the 4th power. So I have an equation here for the ki gain, and then I have k times natural frequency squared times the proportional gain times s, and that equivalent term in my desired characteristic equation is here. And I do the same thing for the 2nd power of s and the 3rd power of s. So I have 4 equations and 4 unknowns. And this makes it very easy. You can do this by hand, by inspection. I use the finder, the equation finder in MathCAD here. So I have ki, kp, kd, and the second derivative gain all in symbolic form. And it's nice to see things in symbolic form. I'm not a fan of using matrices because they hide an awful lot of what's going on. You get numbers without understanding. Here I can see how the gain and the natural frequency affect the different gains. So now I can calculate out the gains that will give me a nice exponential response. Now, one of the things I want to point out here is that if I do the inverse Laplace transform, what I end up with is a equation for the response as a function of time. Now let's assume that r happens to be my target. In other words, I'm moving out to, say, 100 millimeters or some distance. There are 2 parts to this equation. One part is the r times 1. That means that as time goes on, we're going to end up, this is going to decay to 0, so we're just going to be ending up at r, which is what we want. This part here is the transient part, and you can see that it's going to decay as a function of lambda. This is significant. When we happen to use the 4 gains, the second derivative gain, we can make this lambda as big as we want, which basically, because it's going to be a negative term, it's going to move the pole negatively, so we can, any kind of errors or transients are going to decay very, very quickly. This part just determines the ramp, the curve, and how it's going to decay. And the significant thing here is that there's no sines or cosines in here, so that means there's no oscillations. There is a problem with this. You can see that it's possible that if a lambda squared is too small relative to the natural frequency, that the derivative gain can be negative, and that's not desirable. The same thing can happen here with the second derivative gain, but I can tell you that it's usually the derivative gain that goes negative first, so that is the limiting factor. And basically what that means is that the lambda has to be 0.409 times the natural frequency. If you make it the lambda, the poles any closer to the origin than that, the derivative gain will go negative. So what do you do? Well, you can change the desired characteristic equation so there are 2 sets of real poles. There's 2 real poles at lambda and 2 real poles at minus mu. And so I have another set of equations, and I do the same, equating the coefficients. And now I end up with Ki, Kp, Kd, and K2, the different gains here. And what I can do is I can make lambda smaller as long as I make mu bigger, and then that will still keep K2 positive, and I can do the same thing for the second derivative gain. But notice that there's a limit. Mu plus lambda must be equal to the natural frequency, or times zeta, or the damping factor. And so that means that there's a limit to how far positive you can make both gains, or both poles. So basically you use just lambda, 4 poles at minus lambda in the first case, above the breakaway point, which is, this is where the breakaway point happens to be at zeta times omega divided by 2. And then you use, if you want to have a response that's slower, then what you do is you use 2 real poles, and that way you can make this closer to the origin while this one is bigger. So those are 2 good solutions. Now I'm going to try using a PID with all the poles on the negative real axis, but I'm only going to use 3 gains. So I'm not going to use the second derivative gain, and then you can see the problem. Since I have 4 equations and I only have 3 unknowns, I have to use lambda as one of the unknowns, and it solves for the integrator proportional derivative gain, and this is lambda. And this is actually the breakaway point right here. At this point, if you try to increase the gains, you're going to have of the 4 poles, 2 are going to go be complex, and other 2 are going to still be real. And the problem is that if a lambda is fixed at zeta times omega divided by 2, that's going to determine how the poles or the arrows are going to decay. Remember, in the first example, I showed you that there is an exponent to the minus lambda times t. Well, now the exponent is going to be to the minus zeta omega divided by 2. So this is determined by the mechanics and the diameter of the cylinder, the length of the cylinder and the mass. And you can see that the control person doesn't have any choice here. So if you're not using the second derivative gain, this is going to be a recurring theme. You're just going to be limited in what you can do with your response. So no matter how you change the gains, it's not going to make any difference. The response cannot be any larger than this one value. Another thing that I have to notice here is this is not really a valid solution because if zeta happens to be too small, the damping factor is too small, then what ends up happening is that this can be negative, and to stay positive it has to be greater than 0.816, and this is not a normal, this normally will not be a valid solution because the damping factor is usually about 0.3 to 0.4, and I like to use 0.3333, so this is not really a valid solution. So let's try with 2 pairs of real poles. Basically do the same thing we did before. I'm going to equate all the gains, but there's no KD gain here, so I can have a mu here. I can adjust lambda, but you can see that mu is still going to be equal to zeta times omega minus lambda, or essentially lambda plus mu is going to be equal to zeta omega again. And if one is closer to the origin and the other one must move farther away from the origin to compensate so that we don't have any negative gains, but the one that's closer to the origin is going to be the limiting factor. In other words, if mu is moved, or if lambda is moved closer to the origin, the e to the minus lambda t is going to decay slower than what you would have if it was at the breakaway point. So this is closer to the solution that we have where, well, with the other solution where we have two sets of 2 real poles. So let's go back down here. Let's down some more. So the big thing is that we're limited to, for these, to have the fastest response, lambda and mu would both have to be the same value, so that, because if you make one bigger, the other one's going to have to be smaller. And the same value that you'd want them to have would be zeta times omega divided by 2. So if I substitute zeta omega divided by 2 into this equation that I have up above, you can see I get a simplified formula, and lambda and mu are going to be equal to zeta times omega divided by 2. So another problem that we run into is that the zeta must be, the damping factor must be relatively large. If it gets to be too small, there's a problem, and there's an equation for that. If the natural frequency, you have to take the natural frequency and divide it into 2, take the cube root, and that's 0.317 in this case. And if the real damping factor happens to be less than this, then there's going to be negative gains. So let's try another solution where there are 2 real poles and a pair of complex poles. So there's still 4 poles. And here the lambda is the 2 real poles, and I have my complex poles here. This is the real part of the 2 complex poles, and this is the imaginary part of the 2 complex poles. And I'm going to solve, but just like before, I get a Ki, Kp, Kd, and an alpha, but the real part of the complex poles plus the lambda still must be equal to zeta times, well, basically the damping factor times natural frequency. And again, if you want the best response, both real parts have to be at minus zeta times omega divided by 2. And if I do a substitution, you can see alpha is going to be the same as lambda here, and that's going to be 1/2 zeta times omega. So let's try using a PI controller. And what I'm going to do is I have exactly the same equations here as above here. The only thing I'm doing is I'm solving by setting Kd equal to 0, so I get a simpler answer. In other words, this term does not exist. And what I calculate out is the integrator gain, the proportional gain, the real pole, the real part of the complex pole, and the imaginary part of the complex pole. And if you take a look at this solution is the same as the solution above, except for this one's got the derivative, or the derivative term in it. So they're basically the same solution. If I make Kd 0, then I will have the same solution as what I have down here, which makes sense. But let's take a look, go back to when we have the derivative gain, and if I have the derivative gain and I increase it from 0, you can see what it will do is it'll make the integrator gain higher, the proportional gain can be higher, the real part of the complex pole and the real part of the real poles are still going to be the same, and then the complex part of the complex poles, or the imaginary part of the complex poles, is going to be larger. So all you do when you increase the derivative gain is make the response a little bit faster, but it's going to oscillate more, and it's not going to really settle out any faster than if you use the PI controller, because both of them have the same term for the decay. So this might have a slightly faster rise time, but it will not settle any faster than the PI controller. So if you've ever done closed loop control with a hydraulic system and you've tried using the derivative gain and you tried just using proportional and the integrator, and you find that it doesn't make any difference if you use the derivative gain or not, well, now you know why. It really doesn't help to use the derivative gain with the on a hydraulic system unless you go all the way back to the beginning and you use the second derivative gain also. And if you use the second derivative gain, then what happens, you can increase the lambda beyond zeta, or the damping factor times natural frequency divided by 2, and that allows for a much faster response. So let me just give you a small example here. Go all the way down. Now I just want to show what the PI control looks like, and I got my closed loop Bode plot. You can see the derivative term and the second derivative term are gone, or they're missing. And this is actually a fairly nice response. It goes to 10. The reason why it goes to 10 hertz is because the natural frequency of my system is 10 hertz. I chose that value, up here, 2 times pi times 10. So that explains why there's a drop-off at 10 hertz. And you can see that the phase starts decaying pretty quickly, and then it goes to minus 270, and the reason why it does that is because the PI creates 1 0, but there are 4 poles. So altogether, there's 4 poles minus 1 0 times 90 degrees is minus 270 degrees. And then I'm going to do the pole and zero plot. And this is where you have the best response. Now, like I said before, you can usually take the lambda part, the real poles, and you can move these back and forth. But if I move lambda this way, what ends up happening is the alpha term, the real part for the complex poles, goes this way. So what you don't want to do is you don't want to have these complex poles be close to the imaginary axis. So if you have any kind of options, well, this is the best option, but if you want a slower response, you can move the real poles closer to the origin. And what will happen then is that the complex poles will move away from the imaginary axis, and that will mean that you've got a slower but less oscillatory response. Now I'm going to show you what happens with the second derivative gain. I'm using the same gain, natural frequency, and damping factor, but I'm setting the lambda to, in other words, the closed loop poles, they'll be set to a minus, let's see, was it 2 times pi times 10, which is about minus 62. So this is the closed loop transfer function, and I'm going to plot the Bode plot. And here you can see that it's fairly flat. It goes way out beyond 10 hertz, which is where the natural frequency of the system happens to be. And then the amplitude decays down. So we have a bandwidth of about, let's see if that's about minus 3 dB. That's 20, 30, 40, about 40 hertz. Whereas above, that might be minus 3 dB here. You see, this is a different scale. So that might be 3 dB, it might be limited to 10 hertz here. So the second derivative gain is extending the bandwidth by quite a bit. Also, the phase lag isn't as bad. Again, this is a different scale. Remember, we have 4 gains now, so that means we're going to have 3 zeros, and we got 4 poles, so you get 3 zeros minus the 4 poles is minus 90 times 90 is minus 90 degrees, which is what you see here. And this, at first glance doesn't look any better, but you got to remember this is 0 to minus 100 instead of 0 to minus 300, and this is 10 to minus 30, whereas this one is 20 to minus 80. So if I were to plot these on the same scale, the second derivative gain would look a lot better. Let's take a look at the poles and zeros. And you can see that the poles are all four poles are located at well, it's 10 hertz or 62.832 radians. So you're going to get a much faster response. This is the minus zeta times omega divided by 2. And these are the three zeros. The three zeros are responsible for causing these little bumps right here. The zeros will cause a little bit of phase lag or lead and increase the gain. Basically, the zeros increase bandwidth. So, key point here, again, you're limited by the mechanics and the hydraulics if you don't use the second derivative gain. And if you use the second derivative gain, you can extend the bandwidth without too much regard for the hydraulic design and the mechanical design. There are limits though. Feedback resolution is going to be a limit, and also you can't increase the, I'm using a simple model here where I'm assuming the valve is fairly fast, so it doesn't have to be taken into account, because if you have like a slow valve and a slow hydraulic system or cylinder, you'd have a four-pole system, and after you integrate that to velocity to position, that'd be a five-pole system, and we don't have enough gains for that. So there are limits to what you can do, but using the second derivative gain really does help a lot. That's all.